In the last video, we talked about a generic way of converting from decimal to binary, right? But let's go and take a look. Let's take a look at a second method. But before we do, let's just do some binary to decimal conversions. How about converting 3, about 6, 12, 24, 48, 96, and 192. All right, now what we had talked about before was taking our decimal value and breaking it into the power of 2 components, right? So it was kind of like that Bill Gates analogy of light bulbs, turning on light bulbs. So in order to represent 3, well, 3 has 2 powers of 2. It is 2 plus 1. 2 being 2 to the 1, 1 being 2 to the 0, which means that in binary, we have a 1 in the 2 to the 0 place, the least significant bit, right? And then we have a 1 in the 2 to the 1 place, the second least significant bit. Now let's go ahead and make our binary values 1 byte wide, 8 bits. And so that means all the rest of the bits, which should have one more bit here, all the rest of the bits should be zeros. All right. Now, that's easy for 3. It was pretty quick to be able to break 3 into its powers of 2 components. But as we start going a little higher, it becomes a little bit more difficult. 6, still not really a big deal. That is 4, otherwise known as 2 squared, plus 2, right? And so we have a 1 in the 2 to the 1 position and a 1 in the 2 to the 2 position. The least significant bit, 2 to the 0, we still have a 0. We now have a 0. Then there's a 1 in the 2 to the 1 position, a 1 in the 2 to the 2 position, and then we have zeros in all the remaining positions. All right? Now we're starting to get a little bigger here. Breaking 12 into its power of 2 components. Well, it turns out there's still just 2 powers of 2 components. There's 8 and there's 4. All right? 8 plus 4, 12. That means that we have a 1 in the 2 to the 2 position, the 2 squared position, and a 1 in the 2 cubed position. So we have a 0 in the 2 to the 0 position, a 0 in the 2 to the 1 position, but a 1 in the 2 squared, a 1 in the 2 cubed, and then zeros everywhere else. All right? And so we're growing this number, it looks like. Yeah, you probably saw as I was writing these numbers down that each subsequent one is twice the one before it, right? This has something to do with what we're going to be talking about here. 24 is 16 plus 8. Also 2 powers of 2, right? So we have 2 to the 4th and 2 to the 3rd. So that means there is going to be a 0 in the 2 to the 0 position, a 0 in the 2 to the 1, a 0 in the 2 squared, but we have a 1 in 2 cubed, a 1 in the 2 to the 4th, and then zeros everywhere else. These are all binary values, so we'll put our little base 2 after that to make sure we identify it properly, okay? 48. 32 plus 16, which means it is now 0, 0, and then the 2 to the 5th position, 32 has a 1 in it. The 2 to the 4th position, 16 has a 1 in it, and then we have 4 zeros. Notice a pattern happening here? Hope so. 96. This is 64 plus 32. Which is equal to, in binary, 0, 1, 1, 0, 0, 0, 0, 0. All right. And then 192. Turns out 192 is simply 128, also a power of 2, 2 to the 7th, plus 2 to the 6th, or 64, which gives us the binary value 1, 1, 1. Not quite. 1, 1, 0, 0, 0, 0, 0, 0, base 2. All right. Now, what we're looking at here as we are going through and doubling our value each time, notice that basically due to the distributive law, if you multiply 2 times 3 to get 6, that's the same as multiplying 2 times 2 plus 1. Distribute it, you get 2 times 2 is 4, 2 times 1 is 2. And that takes each one of these components, each one of those powers of 2, and shifts them one position up in the powers of 2. It takes each one of these ones and moves them one position to the left, all right? This is actually a very common method of multiplication of specifically powers of 2, but other powers, we'll talk about that a little later in a later episode, but it's a very quick and easy way to multiply numbers without having to use the multiplication unit. The multiplication unit in a processor, especially older processors, the multiplication unit is incredibly slow. There's a lot of hardware involved, it takes a lot of energy, so if you're going to be doing a lot of multiplications, it'd be really cool if we could come up with a simpler way to do this. One of the quickest operations is to just simply manipulate the bits, and there's a number of operations that we'll talk about throughout the semester that programming languages use to allow us to just simply manipulate bits. 2 of them we can actually use here. We have one thing called the left shift operator, and it is just simply 2 less than symbols. That's it. And what the left shift operator does is it takes all the bits of our number and just moves them by the number of bit positions we asked it to move it. So, for example, if I wanted to do A is equal to A times 16, just a little bit of code there, right? So A is equal to A times 16. Well, 16 is a power of 2. And if you look at our 3, we could do 3 times 16 would take us to 48, which means we would need to shift left 1, 2, 3, 4 times. Turns out 16 is what? A power of 4, power of 2 to the 4th, right? So another way of writing this is to simply say A is equal to A shifted left by 4 positions. Notice my semicolons. So I'm writing a little bit of Java code up here. That's what my use of the semicolons are. If you're not familiar with Java, this is true for a lot of programming languages. C, C++, a number of these languages use the semicolon to show the end of a line, all right? Turns out we can divide. For example, what's 92 divided by 8? Quick, 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 quick. Well, turns out it's 1, 2, 3, it's 24. We just simply shift right by the number of 2's that are contained in 8. Now, the right shift operator well, that guy is just simply 2 greater than symbols. And so if I wanted to do something like B is equal to B divided by 8, that is the same thing as B is equal to B right shifted by 3 positions. And turns out that this is such a common thing in our code that if you were to, in your Java code, write this line, more than likely your compiler is going to convert it to this operation. It's going to actually do just the conversion straightforward because the result will be exactly the same, but the execution will be a lot faster. Now, what this does for us is actually gives us another way to do a decimal to binary conversion. And the reason for that is that if you look at these digits as we're shifting these things right, each time we shift right, one of the bits, well, the least significant bit, falls out. It disappears. It goes away. It goes into the bit bucket, so to speak. And this process of shifting and letting those bits kind of fall off the end, we can take advantage of that in order to do a quick conversion from decimal to binary. I'm going to erase these last 2 in order to give me some additional room here on the board. All right. Now, let's do a conversion. Let's convert the decimal number 89 to binary. Now, 89 divided by 2 is equal to, remember, 89 is an odd number, and so we're going to get a remainder. we're going to get a remainder of 1. In fact, that's the only remainder we're ever going to get. We're going to get either a remainder of 0 or a remainder of 1 when we divide by 2. Well, 89 divided by 2 is 44 with a remainder of 1. Now, we take this 44, bring it down here. 44 base 10 divided by 2 is equal to 22 with a remainder of 0. And let's keep track of these remainders. 22 divided by 2 is equal to 11, also with a remainder of 0. All right. 11 divided by 2 is equal to 5 with a remainder of 1. 5 base 10 divided by 2 is equal to 2 with a remainder of 1. 11's an odd number, going to give us a remainder of 1. 2 divided by 2 is equal to 1 with a remainder of 0. And lastly, and we got to do this last step because remember what we're doing is we're shifting the ones out one bit at a time. And what you're looking to do is shift it so that all the ones get shifted out and we're left with the result of all zeros. So we have to do this last division. 1 divided by 2 is equal to 0 with a remainder of 1. All right. Now, all we've done is we've taken 89. In decimal form, yes, but we've taken 89 and shifted the bits out one at a time so that they fall off the end in these remainders. These remainders right here are just simply the binary value shifted out. Now, this guy right here, this is going to be the least significant bit. Remember, the one that represents the 2 to the 0 position, the 1 position, okay? So if I copy these down starting from the right-hand side going up, we'll start with this guy and we'll go 1, take that 0, 0, 1, 1, 0, and then 1. Now this right here is only 7 bits, so we'll go ahead and add an 8th bit to make it so that it is a byte. But this right here, 89 base 10 is equal to 0, 1, 0, 1, 1, 0, 0, 1 in binary. All right. Did we get the right answer? Well, let's do the conversion. This is the 1's place, the 2's place, the 4, 8, 16, 32, that's supposed to be a 2, 64, 128. So this becomes 64 plus 16 plus 8 plus 1. Add all those together, we get 9, carry the 1, 89. And there you go. Quick and easy way in order to do a conversion from decimal to binary using only divisions by 2, keeping track of the remainders.